Somewhere past the edge of everything we can see with our own eyes, a metal probe the size of a small car keeps drifting through the dark. It was never built to come home. That was the deal from day one, back when it first left the Earth. It has already outlasted the people who launched it, and one day it will outlast the country that built it too. Long after all sun swells, dims, and the earth beneath it disappears, this machine will still be out there, carrying a small piece of us forward. This is the story of Voyager 1, where it has already been and where it is headed next, across distances so vast that human time frames barely apply anymore. In 1977, engineers noticed something rare. The outer planets had lined up in a way that would not happen again for 175 years. That alignment meant a single spacecraft could hop from planet to planet, using each one's gravity like a slingshot to reach the next. NASA built two probes to take advantage of this window, Voyager 1 and Voyager 2. Voyager 1 launched second, riding a Titan rocket off the pad in September of that year. But its faster path meant it would actually reach its target first. Packed on board was a full set of instruments, cameras, magnetic field sensors, and detectors built to read the invisible radiation that fills the space between worlds. But one object, bolted to its side, had nothing to do with science at all. It was a gold-coated copper disc, engraved with instructions on how to play it. Inside were images of Earth, greetings recorded in dozens of human languages, and a mix of music gathered from across the planet. A message with no guaranteed audience. The disc also included a map, a way to find our sun using the position of nearby footsteps. Nobody expected this record to ever actually be found by anyone. It was sent out anyway, sealed onto the spacecraft's side before launch. From the moment it left the launch pad, Voyager 1 had only one direction left available to it: outward. There would be no course correction bringing it home. No second trip. Every mile from here on was a mile it would never be traced. 2 years after launch, Voyager 1 arrived at Jupiter, the largest planet in our solar system. Its cameras caught storms bigger than entire planets, spinning endlessly inside Jupiter's thick, churning atmosphere. Bands of orange and white cloud stretching across the whole visible disk. Winds their top 1,500 kilometers an hour, tearing through those cloud bands without even shuffling. The Great Red Spot alone was white enough to swallow Earth several times over, a storm that had likely been raging from centuries before Voyager even arrived. But the biggest discovery of the flyby wasn't on Jupiter at all. It was on one of its moons. As Voyager passed close to Lu, scientists spotted strange plumes rising off its surface, something nobody had planned or expected to see. Those plumes were not dust or gas venting randomly. They were active volcanoes, the first ever found anywhere beyond Earth. Some eruption to material 100 kilometers into space, bright and visible in Voyager's raw, unprocessed images sent back across the solar system. Nearby, Europa looked like a cracked eggshell, Its icy surface, streaked with long dark fractures running in every direction. Ganymede show its own jumbled, complicated terrain, while Callisto appear ancient and heavily scaled. Its surface covered almost entirely in craters. Voyager also measures something completely invisible. Jupiter's magnetic field, far stronger than Earth's arm. It traps charged particles inside radiation belts intense enough to damage unshielded electronics. An environment far harsher than anything a spacecraft would face closer to home. Voyager's instruments flew strapped through that dangerous radiation zone and kept recording the entire time, gathering data that no one had even collected before. Every reading added to a picture of Jupiter that scientists on Earth were only beginning to understand. Then Jupiter gave the little spacecraft one more thing before it moved on. A boost. Using the planet's own gravity, Voyager picked up extra speed, converting a small fraction of Jupiter's orbital energy into momentum it would carry for the rest of its journey. The boost bent Voyager's far away from Jupiter and sent it curving toward its next destination. Without this kind of gravity, a sister mission like this, one would have taken decades longer, or would never have been possible with the technology of the time. In November 1980, Saturn came into view, a planet famous above everything else for its rings. From Earth, those rings look like a single smooth, solid band circling the planet, simple and unbroken when seen through even a good telescope. Up close, Voyager reveals something far more complicated. Thousands of separate ringlets, gaps and grooves, all shaped by gravity and by the pull of small moons hidden within the rings themselves. Nothing about them was as simple as it had looked from Earth. The rings stretch across hundreds of thousands of kilometers, yet they are made mostly of water ice, in pieces ranging from tiny grains of frost to boulders the size of houses, all orbiting Saturn together in a thin, glittering disk. Some of Saturn's small moons act almost like traffic cops, their gravity curving clean, short gaps between sections of the rings. Others are scaled and battered, shaped by millions of years of impacts, their surfaces telling a story stretching back to the early solar system. Some of Saturn's small moons act almost like traffic cops, their gravity carving clean, sharp gaps between sections of the rings. Others are scaled and battered, shaped by billions of years of impacts, their surfaces telling a story stretching back to the early solar system. But one moon mattered more than anything or crater Voyager photographed here. Titan. Titan is bigger than the planet Mercury, and it's wrapped in a thick, hazy atmosphere, unlike anything else in outer solar system, dense enough to hide everything beneath it. It's the only moon in our solar system with air dense enough to completely hide its surface from view. That atmosphere is mostly nitrogen, laced with methane and other carbon-based molecules, similar in some ways to Earth's own early atmosphere billions of years ago. Sunlight breaks those molecules apart high in Titan's atmosphere, and they reform it into heavier, complex compounds that eventually rain down onto the surface below. Scientists still study Titan closely today, largely because of what Voyager first revealed about it here decades ago. To get a close look, Voyager flew near Titan, a move that changed the spacecraft's future forever. The flyby bent its path sharply upward out of the flake plane, where all the planets orbit, and set it on a course it would never leave again. From this point on, there would be no more planetary flybys, no more course-bending encounters. Saturn and Titan were the last close stops on Voyager's journey. Everything after this would be empty space, stretching further than any spacecraft had traveled before it. 10 years later, in 1990, Voyager did something it had never done before. NASA turned its cameras backward towards the inner solar system it had already left far behind, for one final look at the home it would never return to. From nearly 6 billion kilometers away, it photographed the planets one last time, capturing a mosaic that came to be known as the family portrait. In one of those frames, Earth appeared as a single point of light, barely more than a pixel. Every person who has ever lived is somewhere inside that one small dot of light. After that final photograph, Voyager's cameras were switched off for good, to save power for everything still ahead. It would never take another picture again. For the next 2 decades, Voyager kept moving silently towards the edge of the sun's influence. That edge is called the heliverse, the boundary where the pressure of the solar rays gives way to the pressure of interstellar space itself. There is no wall to cross here, no visible line marking the boundary. Voyager couldn't see this edge at all, but its instruments could feel it. A sharp drop in particles coming from our sun, and a sudden rise in cosmic rays arriving from beyond. On August 25, 2012, those readings shifted for good and stayed that way. Voyager 1 had officially left the bubble our sun creates around itself, a region called the heliosphere that had contained every previous human-made object ever launched from Earth. It became the first spacecraft in history to reach interstellar space, the region between stars. Everything past that point was a stretch of the universe no human-built object had ever measured directly before, uncharted in every practical sense. Voyager kept sending data back the entire time, one faint radio signal at a time, crossing billions of kilometers before ever reaching an antenna on Earth. Each signal carried a small piece of what it was discovering alone, far from anyone. Today, in 2026, Voyager 1 sits roughly 26 billion kilometers from Earth. That's far enough that light itself, the fastest thing in the universe, takes a full day just to travel one way between the spacecraft and home, saying a command now, and it will not arrive at Voyager until tomorrow. The reply, if everything works correctly, comes back a full day after that. Every conversation with this spacecraft now takes almost 2 days from question to answer. Meanwhile, its power source is quietly running out. Voyager runs on heat from decaying plutonium, converted into electricity by a system with no knowing pass. And that heat has been fading slowly but steadily for nearly 50 years now. To stretch its life, engineers on Earth have been switching off instruments one at a time, choosing carefully which system to keep alive. Each shutdown buys a few more years of contact with a machine now older than most of the people operating it. Every system still working on Voyager is doing more with less power than it was ever originally designed for, and still against every expectation from its original mission plan. This small spacecraft keeps finding a way to talk to us. Engineers expect that sometime around 2037, 60 years after launch, the signal from Voyager may finally go quiet for good. By then, almost every instrument on board will have already been powered down to conserve whatever energy remains. Whatever science Voyager still returns in its final years will come from whichever single instrument manages to outlast all the others. There will not be a dramatic final message and no warning sent ahead of time before the connection actually ends. One day, a scheduled check-in from mission control simply will not get an answer back. From our side, it will not look like a dramatic death. It will simply look like silence, the same silence that surrounds Voyager everywhere else already. Voyager itself will not know the difference when that day comes. It never actually knew whether anyone on Earth was listening in the first place. It will just keep moving, exactly the way it always has, whether or not we are still receiving anything from it. At that point, Voyager's mission, in any way we can actually measure or track it, comes to an end, but the spacecraft itself does not stop. It simply becomes something we can no longer follow, moving on without us. Skip forward about 40,000 years and Voyager will have a rare kind of encounter. It will pass within roughly 1.7 light years of a star called Galaxy 445, closer to another star than it has been since it left our own sun. That sounds close, but in the scale of space, it's still an enormous gap, nowhere near close enough for anything resembling a real flyby. There are no more gravity assists out here, and no planets left anywhere nearby than Voyager's spot. Between stars, distance simply wanes every time, and even a fast-moving spacecraft effectively crawls. By this point, Voyager's radio has already been silent for tens of thousands of years, and nobody back on Earth is still listening for anything from it. The Andromeda Galaxy, or closest large galactic nebula, has been drifting steadily toward the Milky Way for billions of years already. Eventually, that gap between the two galaxies closest and Andromeda begins to fill more and more of the surrounding sky. The two galaxies begin to pass through each other, gravity-pulling stars into long, sweeping new position across both. Over the course of billions of years, they slowly merge together into a single, much longer galaxy than either one was before. If Voyager could somehow still see, it would witness one of the largest events the universe has to offer, an entire galactic merger unfolding slowly around it, over a timescale longer than the current age of the universe itself.
Roger 192, and Alpha's initiate event.
Now, jump to 10 trillion years from now, roughly 1,000 times the current age of the universe. By this point, the familiar era of bright, massive stars is long finished. replaced by something far dimmer and quieter across the sky. Only small red dwarf stars are still burning by now, sipping their fuel slowly enough to last for this unimaginable length of time. Even they are gradually running out as the raw material needed to form any new stars become harder and harder to find. Galaxies fade into loose collections of dim, dead stars, remnants, scattered across the night sky. If anyone were still there to see it, would grow sparse and quiet. If Voyager has survived this far, it is now older than nearly every star still shining anywhere around it. Beyond this point, we are no longer in the realm of actual observation, only theory. One idea suggests that even protons, the fundamental building blocks of atoms, eventually decay, breaking down after an unimaginably long span of time. If that idea turns out to be true, ordinary matter would slowly come apart. Thanks for watching Future Simulation. Hit that button if you like this video. Subscribe for more.